the next session will go through multiple options for designing a streaming data processing pipeline, comparing Spark structure streaming with Kafka-Streaming, presenting some advantages and disadvantages discovered along the way, and some helpful tips and tricks. And here to share with us on how to leverage power of big data, scalable streaming processing with Kafka-Streams, Kubernetes, and Cassandra to build. And I love this. I love this expression, near real time. Yeah, and we will talk about that. Near real time retail inventory management system. In order to have this shared with us, we have the privilege of having Viorel Bibiloiu, Big Data Architect at eSolutions. Having over 7 years of experience as a full stack developer and software engineer, Viorel's interest shifted towards big data project over the past couple of years, and his current focus being on delivering reliable, scalable, fault-tolerant, and efficient solutions on-premise and on cloud using big data technologies. Having worked with him in the past years and knowing what he knows, ladies and gentlemen, it's my utmost privilege to present to you Viorel Bibiloiu. Please give him a word.
Hello, everyone. Let's start the presentation. First, it's a pleasure to be here. I don't see the presentation. Okay, good. We're all seated after our coffee break. It's very nice to be here. Thank you for the kind words. Okay, today we're going to talk about scalable streaming processing. My name is Bibiloiu Viorel. I'm a big data architect at eSolutions. First, to set the agenda a bit, we're going to see a real-life use case, some challenges in implementing that use case, some options, some pros and cons, and at the end, a conclusion. So, answering the what question, we're going to see how to implement a real-time stock management system for a retailer. This stock management system is going to have some pretty easy to understand attributes. First, we're going to have the store. The retailer has a lot of stores. Then the product ID. This is the unique identifier of the product. Then the inventory quantity. This represents how many items the retailer can sell. And last, the sales quantity. This shows us how many items were sold. So pretty easy to understand. Now let's try to answer the question why. Why is this useful? What are the main points? Well, for a retailer, if we don't have a real-time stock management system, we have multiple pain points. First, we have too much stock. If we have too much stock, we have to pay for, as a retailer, for warehouse costs, but also we can have products that expire, so that's not good. Also, too little stock is bad because we want to be able to sell as many cold beers or ice creams on a hot summer day. And lastly, really being slow in reacting to market changes is bad for a retailer. So that's answering the why question. Now let's think about the how question. Well, an interesting way of solving these issues is to try to think of it as a black box. That means basically thinking about the inputs and the outputs of my problem. So the inputs are going to be different data sources, some streaming, some batch. Then we're going to have the middle part, the black box, without thinking about what technology we're going to use. We just know it needs to be as close to real time as possible and to manage my stock. And then at the end, we'll see that we're going to have different destinations. So that's black box in the situation. Taking it a bit further, I'd just like to add that I have a public service announcement. It's not enough just to build the pipeline. We also have to think about the big data aspect of the pipeline. So there's some non-functional requirements that we need to consider. First, the scalability. We need to think about maybe just adding more resources to our pipeline, or if we can, adding more nodes to the pipeline. We need to keep this in mind when designing the pipeline. Second, thinking about fault tolerance, we need to configure the pipeline maybe just to restart itself automatically if something fails, or even to allow some components of the pipeline to fail and still not having any downtime. Also, a non-functional requirement is maintainability. We need to be able to add new code, new features, or to fix existing features, called bugs, as fast as possible. So we need the code to be maintainable. And lastly, we're also interested in having open source solutions. If we use open source solutions, we have multiple advantages. First, we don't have vendor lock-ins. Second, we're really cost efficient. And lastly, if we use an open source technology which has a large community, the solution itself can be really powerful. But let's take a step back. Let's see some basic use cases to process streaming data. First, a simple use case, ETL. We just take some unstructured data, we clean it, and maybe just insert it in a table in a structured format. So that's the first use case. Another use case can be considered by looking at the output. And for us, maybe an interesting output is a key value store. This is interesting for operational use cases in which I want to give the business side the opportunity to have lookups, or maybe if I want to compute some aggregations, maybe I want to know how many apples were sold in the last 5 minutes. Another basic use case is if we have multiple input streams. So for instance, if I have 2 streams, a stream that shows me the inventory data, and I have another stream that gives me the sales data, my pipeline could just merge the 2 streams and insert the data in another destination. And lastly, we can have a pretty basic use case of change data capture, for which the input side is just a sequence of changes. We take those changes and we will create the source and transactional table for analytical use cases. So those are some basic streaming pipelines. What about our streaming pipeline? Well, it's a combination. We're going to see that at the input side, we're going to have some file sources and some stream sources. And for the destination, it's going to be useful for us to have the data in a key value store for lookups or summaries. But also, we're going to need the data to be in a changelog format to be able to use it later on for machine learning purposes. Seeing our sources a bit in more detail, the first source, we're going to have the inventory data as a file. This file comes every 5 minutes, basically because we don't have the data modified faster than that. And we can get new information in the file if, for instance, we have new products that arrive at the warehouse, or if some products expire. And we see an example of how this file will look here. My second source, the sales, will be pushed in a stream. This will be published by events such as having new products that get sold. So for instance, we can see the first event when the retailer sold 2 products, the second event where the retailer sold 3 more, so 5 in total. And at the midnight, we know that there's a reset for these sales, and I get another event that gives me a sales value of 0, so that I know a new day has started. So those are my sources. Thinking about the destinations, I can see that the necessity is to have some tables in Cassandra, let's say, because it's a distributed database with fault tolerance built in, so it's really good for big data use cases. The first example, quantity by store, could fulfill such necessities like maybe I want to know for one store what is the stock for all my products, and would look something like this. Or if I have another use case in which I need to know for one product in all my stores what is the stock, I can design the table like this. This will be useful, for example, if I want to know in which store for my retailer I can still find the PS5. So pretty common use case. The second destination, a bit more interesting, is having the changelog. This basically represents an aggregated view of the data, and it is needed just to show me how the data evolved over time, my aggregated data. To be able to implement this in my pipeline, I'm going to need something else. I'm also going to need to store the current state of my data somewhere, so that's a requirement, and we'll see how we're going to implement this later on. Now that we've talked about the sources and the destinations, let's see some actual solutions that we tried. First, we tried Apache Spark Structure Streaming, and then Kafka-Streams. Okay, Apache Spark Structure Streaming is really great. It's actually built on top of Spark SQL engine, and it gives us a lot of advantages. We can process data distributed by using workers. We can configure a minimum number of workers and a maximum number of workers, so it scales really easily. It also gives us high throughput, exactly once processing by using checkpointing. Checkpointing is a feature that is used to process data from a stream, and basically if the stream fails, the processing fails, we just know by using that checkpoint where we last processed data successfully, and we can reprocess the data from there by giving us exactly once processing. And also we have some great set of connectors with which we can connect directly if we need to in our Spark Structure Streaming jobs. Now to think about how we write code for Spark Structure Streaming. Developers basically see code like they write code like they would on a batch table. So they just see a subset of the data. They don't see the stream. And Spark Structure Streaming actually runs that code incrementally on the stream. So it's not fancy distributed processing code. It's simple code. And in terms of deployment, typically Spark Structure Streaming jobs can be deployed on a Spark cluster managed by Yarn. But also nowadays we can deploy it on Kubernetes or using a custom scheduler like Volcano. So it gives us a lot of portability. A high-level schematic of such a pipeline will look something like this. We will have the long time running Spark Structure Streaming job connecting directly to our sources. Then the current state saved in something like a Delta Lake. And then having another Spark Structure Streaming job that pushes data to my destinations, be it a key value store, Cassandra like you saw, maybe a Redis, or maybe the changelog. So that's one solution. Is it good? Is it a good fit? Let's see. Well, first, it is scalable. We can configure the workers so that it scales really well. It is also fault tolerant in the sense that we can use the checkpointing, but also we can configure the job to restart automatically, or we can configure the job to have workers that fail. So it is fault tolerant. What about maintainability? Well, we saw that we can write basic bash type code and it's easy to run, so it is maintainable. And in terms of open sourceness, it is open source, it is managed by the Apache Software Foundation, and it has a really strong contributor like Databricks, which make it a great solution. Let's see some pros. Well, high throughput, very low latencies, exactly once processing and great set of connectors. Let's think of some cons. It's hard to find some cons, but I tried to find some. Well, some cons are that it is sometimes tricky to deploy, configure, monitor, and package. We also need another storage for the checkpointing, so it isn't really just one basic solution that we can use. We also have some additional dependencies. And being a strong solution, we sometimes need to tune it a bit better, so we need to understand it, how it works in the background. So some minor disadvantages. Let's think of something else. Again, checking the black box, thinking of how to solve the situation and seeing the inputs and the outputs. We have the stream, the file, and the key value destinations, and again a stream. So a solution came to mind of using Kafka-Streams. Kafka-Streams works really well with Kafka. It's basically a really small library that we can embed in an application. And working together with a Kafka cluster can run really easily without any extra dependencies. We see that we can run it by having an input topic and an output topic. This means the input topic is going to be read by our Kafka-Streams application. Then we do some stream processing, and then the data can be pushed through a sync processor on an outbound topic. Thinking about some goals that were thought of when Kafka-Streams were implemented, well, they basically thought of using what was already existing on Kafka. So basically load balancing and recovering from failures are built in. What I mean by that is that, for instance, if I have a use case which has multiple partitions, partitioning means basically having multiple segments for a topic. So I see an example with 4 partitions, and 2 instances both have the same consumer ID. So that means they consume messages in a scalable fashion, and they don't consume the same messages. If, for instance, I want to scale my use case, I can just easily scale it to 4 partitions, to 4 instances, each consuming from a different partition. And if I have a use case in which an instance fails, recovery is really easily. Those other instances can just process the data. So we have all these great features built in. I also have another feature that we can use. We can save local state in my Kafka-Streams application. This can be used for greater speeds in accessing the data. We don't need now to have data stored somewhere else, incurring a costly network call to get that current data. We can just store it locally, access it really fast, and if that instance fails, I can just recreate the data from the Kafka cluster where it is used as long-time storage. So that's really great. Maybe we can see that we have a challenge now. For our first implementation, we saw that Spark structure streaming connected directly to our input sources, but now we have to push the data on an inbound topic. So how can we solve that? Well, to solve this, but also make us have a lot of power in how easily we can add new features, we thought of using CQRS. CQRS comes from command query responsibility segregation. We saw another presentation earlier about this. This basically means I take everything that can modify my data and turn it into commands. These commands we can see that are at present tense: change inventory, change sales, or delete product. They basically represent something that can happen on my data. And if a command is successful in my pipeline, we get an event. This is at past tense and basically means the command was successful. So we see we have inventory changed, or sales changed, or product deleted. If a command is not successful, we can just log it, but basically it doesn't fire an event at the output side. So those are commands, events. What about queries? Well, the query represents the fact that now we can take the events that get pushed on an output topic, and we can push it to however many query sources we need for different use cases. If we have one use case that needs fast lookup by key, we can use Cassandra. Or if I have another use case which needs fast lookup by all attributes, I can just use Solar or Elasticsearch now really easily. Thinking again about the black box mentality, CQRS with Kafka-Streams would run something like this. At the input side, we're going to have applications that take my input data, turn it into commands, push them on a command topic. Then I'm going to have the middle part, our stock events processor, which will run with Kafka-Streams. And at the output side, I'm going to have consumers that get those messages and push them to however many query sources we need. A high-level schematic would look something like this. We see now that we have an intermediary step which processes the data, sends the data as commands, and then our real-time stock management as multiple instances of Kafka-Streams applications. And then the changes get pushed further along to the query sources. Let's see an example to understand a little bit better how it works. So we see our 2 sources, our inventory file and our sales stream. We can see in turn how these get changed into commands. So we see the inventory, change inventory, the sales, change sales. In the middle part, we're going to have the aggregated view of the data. We see for our product the quantity and the sales. And then at the end, we're going to have the events, the inventory change and the sales change events, which can get pushed to our query sources. We see here how we use the current state of the Kafka-Streams applications to cache our current source and get really fast access. But what's also interesting is that, again, the data is backed up on our Kafka cluster. So we don't care if an instance fails, we can just recreate that data. To see another example, what happens 5 minutes later, when something happens on the inventory side, we get another file. We see some truck brought some more products. We see again how this change gets propagated to the pipeline. We get the commands changing the aggregated state, and this state pushes, again, events to the output. Or if the retailer sells some products, We see again the commands being propagated, changing now the sales quantity and pushing events further along. Let's think again, is Kafka-Streams a good fit for our use case in terms of our non-functional requirements? Is it scalable? It is really, really easy to scale Kafka-Streams. We can configure, as long as we have that maximum number of partitions set correctly in the beginning, we can scale our number of instances really easily, really without any downtime. So it is easily scalable. What about fault tolerance? Well, it is fault tolerant. We saw that we can recover from failures really easily by using the repartitioning. And also, if we just have lower dependencies in our system, we can make the system a lot more tolerant to failures. Thinking about maintainability, we saw that the code is really simple code and it's made to run in a big data fashion by the framework. We can just write simple Java Scala code and it's enough. And it's also open source. It's maintained by the Apache Software Foundation again. And it has contributors like Confluent, which make it again a great solution. We also have an additional feature here of elastically scalability. This basically can be implemented through multiple ways, but two solutions are: one, just take the consumer lag. The consumer lag basically represents if my application that consumes messages from Kafka falls behind. I can take that lag, push it to something like Prometheus, and then just basically use my applications, which are deployed in Kubernetes, for instance, and scale them up and down if I have such lag in Prometheus. Or we can just install something like Kafka-Keda. This is an event-driven autoscaler, and again, can just be easily deployed next to our application, and it will increase the number of applications when needed, when we have new data to process. But there is a caveat. This is good for cloud environments on which we are paying a lot of money for infrastructure. But if we're on-premise, maybe it's not so efficient. If we are on-premise and we have the resources, it's better just to scale the applications from the beginning and use them, because what's the point in having those resources and not paying for them? But as I said, on cloud environments, it's a really interesting use case. Now, a quick comparison of the two. They both are elastic, highly scalable, and fault tolerant. Spark Structure Stream can run together with Yarn, or maybe on Kubernetes with a scheduler like Volcano, and on top of storage like Delta Lake or HDFS, like a really single processing engine. And because we process the data in memory, we get amazing performance. On the other hand, Kafka-Streams is really easy to deploy. We can deploy it everywhere on the cloud or in containers. And also, it's viable for multiple use cases, small, medium, or large. It's integrated to Kafka security. And also, we can just write standard Java Scala code. So they're both great. It's hard to choose from one. Ultimately, we chose Kafka-Streams. Why is a good question? I'm not saying that Spark Structure Streaming is bad. Just for our use case, Kafka-Streams was a bit better. It was really easy to scale and easy to use. And also the fact that we can have no downtime rolling deployments was a really interesting thing that we can use. Now a final schematic of how our pipeline would look with Kafka-Streams is something like this. The input data is processed by multiple producers. These in turn get scaled dynamically by Kubernetes. If we have a Black Friday event in which we need to process more data, we can just scale the producers. In turn, these send the commands to our Kafka-Streams applications, which run on multiple instances, processing them, sending them to the changelog, and then again we have multiple consumers which can send the events to the query sources and fulfill however many use cases we need. And what's great about this is that by designing it this way, we can easily add more input sources, in turn changing them into commands and processing them further along. If we think about some metrics, we managed to process around 50,000 rows per second for more than 1,000 stores and about 500,000 products. So we managed to get to good throughput for the pipeline. Also thinking about applying the pipeline on other use cases, there are a lot of use cases. So basically in healthcare, we can use the pipeline for processing patient data or transactions or test results or consultations. Other use cases, for instance, in IoT, we can process anomaly detection. And again, maybe for retail, we can use it to process recommendations or fraud detection. It's really easy to use. It worked for us at least. And in conclusion, I would just like to say that I'm not trying to say it's generally better than a Spark structure streaming use case. For us, it worked better. It's important for us, basically, when we design such systems, to first understand the use case. It is our responsibility to understand it really well, and then just then try to implement our solution. Thank you.
Do we have any questions? Okay.
Hi, thank you for the presentation. We, in the team I'm in, we have a Kafka-Streams application also, and I'm very interested, like, how do you monitor the consumer group for the Kafka-Streams? How do you know that it consumes everything in the Kafka topics that is pulling data from? How do you know that you don't have lag due to a bigger input and not related to not being the scale that is required for the data that you receive?
Well, basically at all the points in the processing, we just log everything, and we know from the beginning how much data we should process, and then we can correlate the results, and if we have some spikes, we log them, and we can see if we have some anomalies or if the pipeline doesn't work correctly. But it's basically also deployed in more instances that would be needed even for a spike. So that was our use case. Thanks.
Somebody else? Questions?
In the back? Oh, okay.
Thank you for your presentation. I'm also interested in Kafka-Streams, and I was curious, what alternative would you suggest if someone would want to use the benefits of Kafka-Streams or Kafka, but let's say that their architecture, their microservices are not written in Java or Scala?
Okay. Well, basically, so you couldn't even push the messages to Kafka?
Yeah, I could do that, but let's say that you want to do something more advanced, like join, which is supported by Kafka-Streams. And I was curious about your solution.
Well, basically, if you can't use Java or Scala, you can use Spark Structure Streaming, I guess. You have Python support, and you can write your pipeline there, and it's really easy to deploy it now with Kubernetes. You don't need something else. Maybe in the past you needed to have a big platform to run Spark Structure Streaming jobs, but now you can just run it in Kubernetes. So if you have a Kubernetes cluster or something like that, maybe, or in the cloud, you can just configure your jobs with Python, if that works for you.
Anyone else? So you made it perfectly clear.
Thank you.
Thank you.
Thank you very much.